Okay, conic sections, polar coordinates. There's a theorem. Eccentricity is a ratio between the distance between a point and the focus and a line. And if your eccentricity is less than 1, you have an ellipse. If it's equal to 1, you have parabola. And if it's bigger than 1, you have hyperbola. All right, we're all caught up. So now, these are the equations, and let's mess around with this using Desmos. Let's say let d equal to 1, and let's mess around with eccentricity. Let's change eccentricity from being bigger than 1, less than 1, or whatever. So if we do that, we can see if we start off at 1, we get this parabola. How do you know it's a parabola? Well, I guess if you zoom out enough, you kind of see it's a parabola. It never closes in. But once you start getting this to be less than 1, you see that it starts to look a lot like an ellipse. Okay. And if it gets to be bigger than 1, we have to probably have to zoom out again. But you can see the other side coming, the hyperbola on the other side. Right? So that's what happens if you have a sine. If we have a cosine, we'll see that it's just going sideways. We still get the same effects. Except it's sideways. Now let's change the sign. What if the SIGN sign, not the SIN sign? Let's change that to minus. You can see the difference. You see the difference. You see it happen. So that's a plus. Change that to a minus. It just goes on the other side of the line. And you would imagine for the sign, it would go up and down, except instead of the focus going down, it's going that way. Yeah. This is the last section in chapter 10, so I think it's 10.6. All right. Yeah. Oh, there's no homework? Oh, bummer. Oh, that's the get ahead homework. These are called the lab homeworks, by the way. They're labeled 253H. H stands for hours by arrangement. Back when we used to have hours by arrangement. And so the idea is for you to go through these problems before you see them in lecture, so that when you come to lecture next week, you and I would be on the same wavelength. Not like right now where, what? I've never seen this before. So the idea behind the labs is for you to come here. You know how people expect you to read before you come to class? That's what those labs are. Okay. All right. Something interesting about this that we didn't really talk much about. What do you think is going to happen when your eccentricity is equal to 0? I guess it'll just be 0, huh? It becomes a point. It just becomes 0. All right. So that's a general idea. And you could take a look at, there's some graphs in your textbook that kind of describe the orientation and the direction, whether it's going up along the X or along the Y. But one neat thing about this is that the focus point is at the origin. So that's a good thing to remember. Okay. So yeah, your directrix is going to be described by the line D, whatever D is equal to. So X or Y, depending if the directrix is supposed to be horizontal or vertical. I did that wrong. Vertical, vertical, horizontal. I just did a cross thing. Then that's going to be your directrix, and that's an equation where some number is just equal to D. Okay. All right. So planets can usually be described with your in polar coordinates, and here they introduce another set of vocabulary words. So they change the notation a little bit so that we can use another variable here. So the polar coordinate equation of an ellipse with the focus at the origin, because why we're studying this is mainly for the ellipsis. A is the semi-major axis. Eccentricity is E, and the directrix x is equal to D can be written in the form of this. The position of the planets closest and farthest to the sun are called the perihelion and the aphelion, and they correspond to the vertices of the ellipse. So you kind of are able to measure the ellipse that way. And the distances from the sun to the perihelion and aphelion are called the distances, the P and A distances. And so our directrix has something to do with the distance to our directrix, and eccentricity has something to do with the distances between the focus point and the graph and the vertex. And so that's how they get the connection. So what I'd like to do is have you guys think about how to write the equation of the orbit of the Earth going around the sun using polar coordinates. So anybody know the eccentricity of the Earth off the top of your head? Benny's thinking about it. It's less than one, right? It turns out that it's really, it's almost like a circle, and you know that as the eccentricity gets closer and closer to zero, it becomes more of a circle. So it should be probably like 0.1 or 0.01 or something like that. So let's find out. Did you know that you can ask Wolfram almost anything? Oh, you can Google too, I guess. But we can see the current distance of the Earth from the Sun. And the largest distance and the smallest distance, what are they called again? Perihelion and aphelion. So we have our perihelion and aphelion here. Our orbital period, we could take a look at that if we are interested in, we decide to transform this into polar coordinates where we change the period. Instead of going around to 2 pi, we change the period to, what is it, 365.25. 0.25, right? That's your leap year every 4 years. And eccentricity was 0.01. All right, so take a couple of minutes, see if you can write down the equation for the Earth going around the sun. So the eccentricity is 0.01, and then I'll write down the perihelion, the aphelion, and the perihelion. Well, it turns out that you don't want to use A, you want to use A times 1 minus E as the whole thing. And this is 1 minus E squared, so I don't know, do some math there to figure out how to relate those things. Something about factoring a perfect difference of perfect squares. All right, let me capture the other one. What? Let's use should we use million miles, or it doesn't matter as long as you label it correctly. So AU is astronomical units, like, is that light years or something? And wouldn't that be a light year? No. Yeah. It's the amount of time. Oh. Well, the distance from the Earth to the Sun apparently changes, right? So it's not one. But if you look at the largest and smallest, it looks like it's a little bit bigger than one, a little bit less than one. So there's average distance. So anyways, we can use astronomical units, the AU, and so one of them is the aphelion, the other one's perihelion, and you can figure out what their eccentricity is. And then from there, you can probably figure out what the directrix is. But let's see. All right. I haven't written anything yet. Well, let's see if we can write it down. So we have R. R is equal to A divided by 1 or times 1 minus E squared all over 1 plus E cosine theta. So we know the eccentricity is equal to 0.0167. Let's just say 0.017. And let's use astronomical units. The farthest from the sun is the peri. So the distance away from the sun, perihelion, is going to be A times 1 minus E is equal to what? What is A? A is just a variable right now, parameter. So that's equal to 1.017. 1.017. And the aphelion A1 plus E is going to be, yeah. Mm-hmm. E is less than 1 is what we, for an ellipse, E is less than 1. Yeah. Oh, yeah, it should be. Yeah. Well, I don't know what A is at this point. So, oh, perihelion is shorter distance? Oh, so this is backwards? All right, so I think that might be true. So 1.017 here, and then the other one is the smaller one, 0.983. So if we know what E is equal to, we should be able to figure out what A is equal to. Yeah. And then, but then, yeah, if you multiply them, you'll have A squared, right? So I think if you just figure out what E is equal to, so let's say A1 minus 0.017 is equal to the 0.983. What's A equal to in this case? Yeah, so what's 0.983 divided by parentheses 1 minus 0.017? Anybody in the calculator? Is it 1? So this is a case where A is equal to 1. So I think that's it. So we should be able to graph it. Let's graph the Earth's orbit. So what was it on top? 1 minus E was divided by, and this is a plus, and we use cosine. There we go. Looks a lot like a circle. But we know it's not, right? It's just an ellipse with a really, really small eccentricity. So imagine plotting this out, and imagine plotting out the moon and see the sun going around the moon. I mean, the Earth going around the sun and the moon going around the Earth at the same time. It's a cool picture. All right, see you guys Monday.